In this video, we're going to revise the three AS reaction mechanisms. So that's radical substitution, electrophilic addition, and nucleophilic substitution. So the example we'll use for radical substitution is based around the reaction between propane, so C3H8, and chlorine. In the presence of UV light, that's going to create chloropropane and hydrogen chloride. So what would the mechanism look like for this mono-substituted product? And then we'll go into further substitutions at the end of this. So there's the first step, the initiation step, and that's when your halogen, so chlorine in this case, is exposed to the UV light, and the UV breaks the covalent bond between the chlorine atoms and produces these two radicals. This is an example of homolytic fission. So fission, breaking of the covalent bond homolytically, because each particle produced receives one electron from that covalent bond that's broken. You'll notice I haven't put the dot on there. OCR don't seem to bother about the dots. We'll put it in if you want. So there it is there. So the next set of steps are called the propagation steps, and you can see in brackets there I've written in pairs. So this is actually the first of the pair. So you think of it as P1, propagation 1, and that's when your chlorine radical strips out one of the hydrogens from your alkane molecule to produce a hydrogen chloride molecule and generating a new free radical. So this free radical will feed into P2. That's going to combine with some chlorine that hasn't been broken up into radicals, and this is going to strip off a chlorine atom to stabilize itself. So you'd get C3H7Cl, and this would be now in the form of a chlorine radical. And the final step is a termination step, and again in brackets I've written more than one possible, and that's because all a termination step involves is the combination of two radicals to create a stable molecule. So there are actually three possible termination steps here. We could combine two chlorine radicals, so Cl dot plus Cl dot to make Cl2. We could combine a propyl radical and a chlorine radical, so Cl dot plus C3H7 dot to give C3H7Cl. And we could also combine two propyl radicals, C3H7 dot plus another one, and that's going to give C6H14. So you might get at the end of the question, suggest why small amounts of hexane are also formed in this reaction, and that would be the reason there, because of this termination step that's possible. Another question that they might tag on at the end is suggest why this wouldn't be a great synthetic route, and that leads back to what I was saying at the start of the mechanism. This is mono-substitution. One chlorine is substituted with one of those hydrogens. It's possible for further substitutions to take place, so we'll look at that now. The problem arises when you've got your halogen in excess. So as soon as you've made your mono-substituted product, the chloropropane, another chlorine radical can come along and take out another hydrogen. And that would give this first propagation reaction, and then the radical that's been formed in this first propagation reaction can feed in to the second propagation step. Remember, these always occur in pairs. Can react with more chlorine and produce this dihalogenolcane and another chlorine radical. And essentially that can continue, it's a sort of chain reaction, until all of these hydrogens have been stripped out. But each hydrogen comes out one at a time in this pair of steps. The example we'll use for electrophilic addition is this reaction here. So that's propene with hydrogen chloride to make chloropropane. So there's the propene molecule and the hydrogen chloride. You can see I've put the dipole on the hydrogen chloride. Chlorine's more electronegative than hydrogen, so the dipole's this way around. So what's going to happen? The pi electron pair from the double bond comes out and is attracted towards the slightly positive hydrogen. So just make sure that your curly arrow starts in the middle of the bond there, not from one of these carbons, and that will repel the pair of electrons that are already tending towards this chlorine. It'll completely push them on, and effectively it'll break that bond. The type of bond breaking is heterolytic fission, and that's because the chlorine receives both of the electrons from the bond. Now I've deliberately chosen propene so I can make this point here. Because this is an unsymmetrical alkene, the hydrogen can actually create two possible carbocations. And so the top example here, the hydrogen is attached at the end there, and that's generated this carbocation, which we would call a secondary carbocation because the carbon with the positive charge has two carbon groups directly attached to it. So that's when the hydrogen goes to this carbon here. The hydrogen could also attach to this carbon here. So essentially we've put it here, and that means that the positive charge is now on this end carbon, and so this carbocation is what we call a primary carbocation because the carbon with the positive charge has got one carbon group attached to it. And you can see on the far right there, the chlorine that's come off is in the form of a chloride ion. So the final step of the mechanism, the lone pair of electrons on the chloride ion would be drawn towards the positively charged carbon in the carbocation. So in the case of the secondary carbocation, your curly arrow would go from here to here, and that would obviously produce 2 chloropropane as a product. And for the primary carbocation, the curly arrow would go from the lone pair on the chloride ion to the positively charged carbon and produce 1 chloropropane. The 2 chloropropane would be the major product, and that's because the secondary carbocation that was here before the product is more stable than the primary carbocation that would form the 1 chloropropane. So we'll get a small amount of this, we'll call this a minor product, lots of this, major product. The rule that I've followed there is Markovnikov's rule, which basically says that the hydrogen will add to the carbon which already has more hydrogens attached. So if we go back to the start here, this carbon has 2 hydrogens on, this one only has 1. So the hydrogen prefers to go to this carbon here because it produces the more stable carbocation. And it's called electrophilic addition because basically the mechanism involves what we call an electrophile. That's an electron pair acceptor. So you can see that this HCl molecule here, essentially the hydrogen, is accepting a pair of electrons, and so it's an electrophile. Addition because we are essentially adding the HCl molecule across the carbon-carbon double bond and turning these 2 substances into the 1 product. For the nucleophilic substitution example, we'll look at the reaction between chloroethane and sodium hydroxide to produce ethanol and sodium chloride. So there's the chloroethane with the dipole across the carbon-chlorine bond. Remember, chlorine's more electronegative than carbon. And for the purpose of the mechanism, we're only going to show the hydroxide ion, not the full NaOH. So you can see I've got the lone pair drawn up there on the oxygen. So that will be attracted to the carbon, and that will repel the pair of electrons straight onto that chlorine, and it will break this bond here by heterolytic fission. Nice single step mechanism. We've got the product here, the ethanol, and this Cl would now be in the form of Cl minus. So if you think about the sodium ions that would also be present here, they're not actually taking part in this mechanism, that would then generate sodium chloride as a result. And the mechanism is called nucleophilic substitution because we have a nucleophile involved, and that's an electron paired donor. So you can see from the mechanism the hydroxide ion is donating a pair of electrons to that slightly positive carbon. Substitution because we are swapping the Cl for the OH.